Oh, thank you for joining us. This is YouTube recording of Association of Women Geosciences Pacific Northwest Chapter. And we have a guest speaker, Dr. Jamie McDonald, who's a professor of geology from Florida Gulf Coast University. Today is Saturday, June 7th, 2025, and he is our invited speaker who's going to talk on tectonic development of the polygenic Ingalls Ophiolite complex. I want to give a little introduction to Jamie. I had first seen him, seen his work, but also he is a frequent on Nick Zentner's YouTube, and thought he spoke in an exceptional way and he was generous enough to take up our invitation. He holds a PhD in petrology, geochemistry, and tectonics from the University of Albany State University of New York, and has a BS in environmental geology from New Paltz State University of New York. Since 2007, he's been a professor at Florida Gulf Coast University and a full professor since 2018. He's been doing research in the North and Central Cascades since 2001. So that's in Washington, right where we're going to have him talk about, and has also done research in the Klamath Mountains, such as the Josephine Ophiolite, but much of his work has focused on arc rocks and ophiolites. And he will explain what those are. If you don't know what they are, you will by the end of this talk, and it's fascinating. In particular, the Ingalls Ophiolite complex. Now, that's a favorite place of mine because it rims Mount Stewart batholith, which is in the North Cascades, central North Cascades, and the famous Enchantments Peaks areas, which is a favorite for hiking in the summer. And to understand this will be terrific. Dr. McDonald has been interviewed by Nick Zentner about the Western mélange, including Ophiolites and early Cascades of Washington. And also, he has been talking about the shucks and blue schist. So I invite him to give us our talk.
Mindy, thank you so much. That was an excellent introduction. I'm a little embarrassed. You made me sound so accomplished. And Nick is very generous. I also talked to Nick about the Mount Persis, the volcanic rocks of Mount Persis, which are some Eocene volcanic rocks that are in the breakoff belt story with Jeff Tepper. So I'm going to share my screen, and let's see here, share. Okay, good. Everybody should be able to see that, okay? Let me hide this little floating meeting control, and we'll put that into presentation. Can everyone see that okay?
Yeah, it looks great. It's in presentation.
Oh, okay, great. And so, so this picture is of Esmeralda Peaks proper. Hold on one second. Let me get the little laser pointer started here. And so this is Esmeralda Peaks proper. The Esmeralda Peak Basin trailhead parking is right down here in this little valley. That's Coppin Peak. And this is Hawkins Mountain over here. And so I'm standing on Long's Pass looking back to the southwest. It's hard to see, but that's Mount Rainier right there. And Mount Stewart is to my back. And so these are beautiful rocks that occur within the Wenatchee Mountains in the Central Cascades of Washington State. But I wanted to give a bit of an overview and thank some contributors. On the left here is Bob Miller. Bob's a retired professor from, oops, sorry, Bob, I got a laser pointer on your face. Bob's a retired professor from San Jose State University. And Bob is the only person who has been studying the Ingalls Ophiolite longer than I. Bob started working on the Ingalls, I think, in 1974, maybe even before that. Bob did his PhD at the University of Washington on the Ingalls Ophiolite. To Bob's right is Greg Harper. Greg was my graduate advisor at the University of Albany. Greg passed away last November. It's very sad. I'm going to miss him tremendously for the rest of my life. And he was a wonderful mentor. Greg was an ophiolite expert. Greg worked on ophiolites in Wyoming. He worked on ophiolites in Italy. He worked on the Ingalls Ophiolite, but he's best known for work on the Klamath Mountains on the Josephine Ophiolite. And then we had a number of people from San Jose State University also work with us in the past. Jonathan Miller, who's a professor there, some of Bob's graduate students, Ante and Cindy. And then I had a couple of undergraduate students, Scott and Christy from Florida Gulf Coast University, work on the Ingalls Ophiolite over the last few decades. And so just this talk is happening because of all the contributions from all these different people. I'm stealing lots of their pictures, lots of their data, but this was all done collaboratively, so I feel comfortable utilizing their material, and I'm acknowledging them here. Please excuse me as I sip my tea. So first I thought, let's talk about what an ophiolite is. And so this is a little tectonic cartoon from a textbook showing the idealized creation of oceanic crust and mantle at a fast divergent plate boundary. Fast just means the velocities between the two plates are at the higher end of the velocities that can occur at divergent plate boundaries. And so you have shallow mantle melting. Shallow meaning the mantle melts about 60 kilometers or about 35, 38 miles below the surface. And then the partially melted mantle rises towards the surface, and you have a shallow magma chamber that's only 2 to 4 kilometers or like 1.5 to 2.5 miles below the surface of the Earth. It erupts as a linear vent volcano. And these vent volcanoes at divergent plate boundaries, these are the most common volcanoes on Earth. We tend just not think about them because we can't see them, because they only come to the surface at one place, and that's in Iceland. Every other divergent plate boundary, every other vent volcano at a divergent plate boundary is deep below the ocean surface, 2 to even more kilometers below the surface of the ocean. There's lava flows at the surface. There's multiple intrusions of diabase, which is a transitional rock between basalt and gabbro. And then the magma chambers crystallize in gabbro. And then the residue, the mantle that's left over after partially melting, becomes the lithospheric mantle of the ocean. And so there's the lithospheric mantle of the ocean. There's the gabbro that forms in the magma chamber. There's the diabase that forms as repeated injections of igneous rocks at shallow depths, but not right at the surface. And then there are pillow basalts and massive lava flows forming at the surface. So you get this sort of pseudo section, is what we like to call it, where you have extrusive lavas at the top, and then you have these hypabyssal rocks, these transitional rocks, these diabases. If we were in Europe, we'd call them dolerites, but in the United States, we call them diabase. One of the reasons is because dolerite sounds too much like diorite, but diabase sounds like diorite too. Anyway, it's a transitional rock between basalt and gabbro. Transitional as in its grain size. It's too coarse to be a basalt, but not, the minerals aren't quite large enough to be a gabbro. Then we have our gabbros forming in the magma chamber. And then we have our peridotites. And harzburgite and lherzolite are types of peridotite, but we'll look at that in a second. So when you have oceanic crust forming at a divergent plate boundary, you get this pseudo section and this pseudo stratigraphy. We call it pseudo stratigraphy because their igneous rocks are not supposed to have stratigraphy, because sedimentary rocks have stratigraphy, not igneous rocks. But because of the common layering of basalts at the top, then into these dikes, and then into the gabbro, and then the mantle rock peridotite below, we call it a ophiolite, oceanic stratigraphy. Ophiolites. So ophiolites are sections of oceanic lithosphere. So the crust and the mantle. Let me go back one slide. So these three rocks are the crust, and this is the mantle, right? So the basalt, the diabase, and the gabbro are the crust. There's the crust. And then the peridotite, the harzburgites and lherzolites are peridotite. The peridotite is the mantle. So there's the mantle. So together, that makes up the oceanic lithosphere. So when sections of the oceanic lithosphere get emplaced onto continental margins, we give them a special name, call them Ophiolites. They have the same pseudo-stratigraphy as the oceanic lithosphere. This is a picture from the same textbook. It's showing the basalts at the top into the diabase dikes and then the gabbro. It's showing different kinds of gabbro, some gabbro that's layered, some gabbro that's quote unquote massive. Massive just means sort of regular looking gabbro that you would see in like a petrology lab class or something like that. Layered means that the minerals settled out. And so this right here is pictures of layered gabbro. And then rhyolite and dunites are really fancy kinds of peridotites. And then more peridotites, harzburgites, and dunites, and things like that at depth, which are more peridotites. So these all represent the mantle. So this is the transition between the crust of the mantle. All these rocks up here are crust. All these rocks down here are mantle. And so ophiolites are sections of oceanic lithosphere, crust and mantle, that have been placed onto continental margins. And they get in place through convergent tectonic activity, through collisions. Divergent plate boundaries form all over the Earth. Here's the Mid-Atlantic Ridge, here's the East Pacific Rise. And the colors here are associated with the velocities at which the plates are moving apart. You have the green is actually a combination of fast and medium velocity divergent plate boundaries. The fastest plate velocity on Earth is a divergent plate boundary along the East Pacific Rise. It's about 18 centimeters a year. And then you have slow, and the Mid-Atlantic Ridge and the Indian Ridge are mostly slow. And in the last 20 years, they came up with a new classification, and they call it ultra slow. So these are divergent plate boundaries that are very, very slow. You see them in the North Atlantic and the South Atlantic, where they're really close to the points of rotation of the plates about the divergent plate boundaries. So the closer you get to the point of origin of the plate motion, the slower the velocities get. And so you have in both the northern and southern Atlantic and southern Indian Ocean, you have ultra slow divergent plate boundaries. So you can get these different velocities at divergent plate boundaries. Normally, when we show a picture of a divergent plate boundary, we're showing a picture of a fast divergent plate boundary because that's that's the neatest looking one, I guess. And so here are 3 cartoons of what divergent plate boundaries look like in cross section. A fast spreading ridge has that very traditional oceanic crust assemblage that we saw in that cartoon from the textbook, where you have the lavas or the pillow basalts at the surface. You have the dikes, the diabase just below that. Then you have the plutonic rocks, which are gabbro. You have this large magma chamber, but only a small melt lens of magma. And then below that, you have the moho, the transition between the crust and the mantle, and then you have the peridotites. At a slow divergent plate boundary, you have much more accommodation, much more of the motion is accommodated by normal faulting. Because they're areas of extension where 2 plates are moving away from each other in opposite directions, that's where you get normal faulting. And so a large amount of the motion can be accommodated by normal faulting. And you'll still have the same section. You'll have the basalts, the lavas at the surface, then the diabase dikes below, and then the plutonic rocks here are again gabbro, and then you have the mantle peridotites. But you have a lot more faulting. At ultra slow, you have very little magma, and you have a disrupted crustal section. With sometimes you can expose the mantle right at the surface through a core complex, through a low angle normal fault that faults away the crust and exposes the mantle below it. At an ultra slow divergent plate boundary, the plate velocities are so slow that you can actually accommodate all the plate motion just by faulting. You don't have to create new oceanic lithosphere by magmatic activity. And so we always show this sort of idealized fast velocity in these tectonic cartoons, but truthfully, there's lots of different things happening here. And you can get slow with a lot of faulting, you can get ultra slow with a lot of faulting. There's transform plate boundary settings for oceanic crust and lithosphere. And so they're not all perfect. And so when we think about ophiolites, we have to keep this in mind that the oceanic geology itself is very complex, and you can have different geology based on your tectonic setting. And so when you look at pieces of the oceanic lithosphere that are now preserved on continents, you shouldn't assume that they're all going to look the same and have the same pieces and the same perfect section that we always expect them to have. Because the idealized ophiolite is also from a fast spreading ridge where you have lots of lava at the top, and then lots of diabase, and then lots of gabbro, and then a very voluminous mantle section where if you were forming your crust at an ultra slow spreading center, you might not have that. You would have a lot of mantle exposed, you have little random blobs of gabbro here and there, a lot of diabase cutting through the mantle section and stuff like that. So how do we preserve oceanic lithosphere if in a convergent tectonic setting, it's the oceanic lithosphere that subducts? And it subducts because its density is greater than the continental lithosphere. It's not supposed to be able to move up onto the continental margin. And so this was sort of a fundamental question that needed to be overcome in the 60s and 70s when they first were making the connections between the ophiolites that they saw on land and the things that they were discovering at divergent plate boundaries in the oceans. And now we know that you need some sort of, it's easiest to do if you have some sort of backstop. And the backstop, something of low density that's going to force oceanic crust up onto the continental margin, is probably going to be an oceanic island arc, like the modern day Tonga and Laos and the Marianas Islands, or the Lesser Antilles in the Caribbean, or the Sandwich Islands, those delicious islands in the South Atlantic. You need something of low density that can trap the oceanic crust or force the oceanic crust and lithosphere up onto a continental margin. And so here are just three examples of how you might make an ophiolite. And the first one's called abduction. Here you have an oceanic arc, and you have oceanic crust in front of that arc, and that's called a forearc because it's in front of the arc, F-O-R-E-A-R-C, forearc. And again, the volcanoes, the oceanic island volcanoes that are created by convergent activity are called arcs because on a map view, they're curved because the Earth is round. And so they don't really have much of a choice. And so, so they're arcs, so the volcanoes are the active arcs. And this volcano can act as sort of a backstop and sort of push the oceanic lithosphere up onto the continental margin if the arc itself starts migrating towards that convergent tectonic setting. And that's called abduction. And supra-subduction zone just means it sits on top of a subduction zone. And so it's an ophiolite that formed above a subduction zone. It was forced up onto that continental margin because the volcanic arc acts sort of as a backstop and sort of force it up there I don't know, like a backstop. And the middle one is the collapse of a marginal basin. This right here is the marginal basin. There is the oceanic plate subducting. This arc and marginal basin are attached to this continent. If these sections, this continent collision occurs, it's going to take that arc, the marginal basin, which is oceanic crust and lithosphere behind it, and it's going to force that up onto the continental margin. And so you're gonna again, it says supra-subduction zone ophiolite. You're going to take this oceanic lithosphere that formed above a subduction zone, and you're going to force it up onto the continental margin because the arc itself is also faulted up onto the continental margin. And the arc acts as a bulldozer and just pushes that oceanic lithosphere up onto the continental margin. The third example here is the hardest to do. because what you're doing here is there's the divergent plate boundary. And the divergent plate boundary is the thinnest and tallest and hottest part of the oceanic lithosphere. And because it's young, it has a lower density than the rest of the ocean basin. It has a high temperature because of the magmatic activity that's occurring, and it's thin because it's thin lithosphere and crust that's still forming through at a divergent magmatic activity. Excuse me while I drink my tea. And so the oceanic ridge, the divergent plate boundary itself, can get sort of scraped off and accreted or stuck into the forearc where the rest of the plate continues down into the mantle. So this third one is the abduction of a young, thin, and hotter ridge during subduction. So these are just 3 examples. There's actually a lot of ideas and ways that Ophiolites can get preserved. I have a personal bias. I like the one in the middle the most because, like Mindy said, when I first started working in the Klamath Mountains, I looked at the rocks that were associated with the Josephine Ophiolite. And the Josephine Ophiolite, this would be the Rogue Checo arc of the Josephine Ophiolite. That would be the Josephine Ophiolite. This is the North American margin. And then that arc forced the Josephine Ophiolite up onto the North American margin and preserved it. And so this collapse of a marginal basin that's flanked by an outboard arc is a really easy way to preserve oceanic lithosphere. These other ones take a little more effort. This one's the simplest, but they're all possible. I'm going to talk about geochemistry, and I thought it would be good to sort of do an overview of what I'm talking about before I talk about it. So let's start here at our divergent plate boundary. The mantle is rising, the asthenosphere. The asthenospheric mantle is rising from below to fill in the space left behind as the 2 plates move apart. The asthenospheric mantle starts to decrease pressure at a higher temperature than, I'm sorry, I misspoke. The asthenospheric mantle starts to decrease in pressure at a higher rate than its temperature decreases. And so it will partially melt due to an adiabatic process. Its pressure is decreasing at a tremendous rate, so it's decompressively melting. This happens fairly shallow at like about 60 kilometers below the surface of the Earth. The partial melting begins. The magma chamber itself is only 2 to 4 kilometers below the surface of the Earth. So the melting happens at about 37 miles, and the magma chamber sits only about 1 to 2.5 miles below the surface of the Earth once it partially melts and then the magma forms. You can only partially melt the mantle because the Earth is no longer hot enough to completely melt the mantle. It's very difficult to completely melt the mantle. If you were to completely melt the mantle, you would make an ultramafic magma because the mantle is ultramafic in composition. When you partially melt the mantle, you only take part of the ultramafic mantle out, and so that's why you make a mafic mantle. And it's really nice alliteration. And I make all my students say this over and over again in the upper division classes. But everybody knows that partially melted mantle makes mafic magma. And so there you go. So when you're partially melting the asthenosphere, you'll make a mafic magma. At a hot spot, see, I wrote shallow here, I wrote deep under the hot spot. At a hot spot, the mantle melting occurs much deeper. The partial melting of the mantle occurs much deeper. It occurs between anywhere from 400 kilometers below the surface to 100 kilometers below the surface. The partial melting begins. Because it's so deep, there are certain elements that are not allowed to go into the magma. For example, really deep in the mantle, garnet will be a stable phase. And garnet likes certain elements like yttrium and ytterbium, lutetium, these really strange heavy rare earth elements. We're shallow in the mantle. The most common aluminum mineral phase is plagioclase, and plagioclase doesn't really care about those elements, and so they'll melt out in equal amounts. And so the deeper you melt, you can actually change the composition of the magma slightly. You're still making a mafic magma. It's the trace elements that are slightly different. at a convergent tectonic setting, all these little blue arrows are trying to show water and other volatiles leaving the downgoing plate between 100 and 150 kilometers below the surface of the Earth. They hydrate the mantle that sits above them, the asthenosphere. The water acts as a flux and it lowers the melting temperature of the mantle. So the mantle partially melts, and the partially melted mantle rises to the surface and either forms an island arc or a continental arc. These arcs are normally more intermediate in composition because of assimilation, fractional crystallization, and magma mixing, as opposed to the mafic magmas you'll get at a divergent plate boundary and the mafic magmas you get at hotspots, like Hawaii. And so these are just some basics about partial melting of the mantle and the kinds of magmas you can make, because we're going to revisit this at the end. So Ophiolites, there are a bunch of Ophiolites that occur along the Cordillera and the west coast of North America. The Coast Range Ophiolite is a large accumulation of a multitude of Ophiolites that are sort of similar in age. They're about the same age. Then you have the Smartville, which is an arc Ophiolite. Then you have the Josephine Ophiolite, the Oregon Coast Range Ophiolite, and then we have our ophiolitic rocks up here in Washington State. This is a picture, just because we're in the Pacific Northwest. This is a picture of Esmeralda Peaks, but just now we're this is Gallagher Head Lake right here. Now we're facing east from the west, and so we're almost facing dead east. Coppin Peak is off out of the frame. Mount Stewart is off to the left here out of the frame. And so it's just another picture of Esmeralda Peaks from a different perspective. So there's a huge number of Mesozoic Ophiolites all along the west coast of North America. And they're there as part of the multitude of accreted terranes that make up the accretionary orogeny that developed the west coast of North America. So these Ophiolites got all caught up within the accreted terranes. So we're going to zoom in. We're going to look here in the Pacific Northwest. So this map has some color. Maybe the color is a little distracting, but the ophiolitic rocks are black. So here's the Ingalls Ophiolite. That's the Mount Stewart batholith that intrudes it. There's the Windy Pass thrust, where the Ingalls is thrust over the Cascade crystalline core, essentially thrust over the Chewacum schist of the Cascade crystalline core. The Ingalls is not the only ophiolite in Washington State. We have the Fidalgo Ophiolite complex in the San Juan Islands, which is also Mesozoic in age. And then we also have the Twin Sisters dunite, which is a large ultramafic complex, which has affinity, has geochemistry that suggests it formed above a subduction zone. And it essentially represents the mantle of some sort of subduction zone setting. But because the crustal pieces of the Twin Sisters is missing, we don't really know too much about the Twin Sisters. We also don't have a good understanding of the Twin Sisters' age. But it's a giant blob of ultramafic rocks. It's really awesome, and it's there. So the two main ophiolites here are the Fidalgo and the Ingalls. The Ingalls is far superior, and I'll tell you why in a second. There's also some quote unquote ophiolitic rocks, like the Easton Metamorphic Suite has rocks that kind of, very similar to what you would find in ophiolite. If anything, it might be the crustal section of oceanic crust that's now deformed in green schist and blue schist facies. So a higher temperature metamorphic rocks. In the Helena Haystack melange, you have some serpentinite melange with diabase and basalt that are, well, I'm sorry, woodpeckers pecking on the side of the house, with ultramafic and diabase and basalts that are caught up in a serpentinite melange. And so that may or may not be highly dismembered oceanic crust. And there's some other things too that kind of look like ophiolitic rocks in Washington State. But the Ingalls is by far the most superior here. So just to orient ourselves, here's Cleellum. This is Highway 97. This is US 2. Wenatchee's off over here. Ellensburg is off over here. Here's Interstate 90. That's the Snoqualmie Pass right there. And then there's Seattle. So we're going to zoom in on the southern portion of the Ingalls Ophiolite. So the Ingalls Ophiolite is the most complete ophiolite and the largest ophiolite in Washington state. It's also probably studied a bit more than the Fidalgo, at least more modern studies on the Ingalls. The Fidalgo was studied heavily in the 70s and 80s. There's Mount Stewart batholith, which is Cretaceous in age. There are some satellite plutons of the Mount Stewart. This one's called the Fortune Creek Stock, which is just kind of a cool name. There's this odd little thing that we just won't talk about called the Drew unit that Bob Miller discovered and I also worked on. The Drew is kind of this weird thing that looks a lot like the Western Melange belt. It's enigmatic because we don't have control of its age. It's a higher metamorphic grade than the rest of the Ingalls, and it has different lithologies, different rock types than the rest of the Ingalls. So it just seems to be faulted against or within the Ingalls. The Ingalls is essentially a mega melange. These giant crustal blocks of basalt, diabase, and gabbro that are within a serpentinite melange. So they're within an ultramafic melange. And the foliations in the melange, just like my little squiggles, run pretty much east-west. And the crustal blocks are faulted within this melange, and they dip steeply, mostly to the north. I'll go into more detail of the units in a second, but let's look at our cross section. So over here, we have a cross section from A to B. This Ante created when he was working on his master's thesis, and he very kindly allowed me to use it several years ago, so I thank him for that. And it shows the cross section through what would be Highway 97 comes through the Ophiolite over here. So Highway 97 will be hiding down over here. This would be like if you're hiking along the Ingalls Creek Trail head towards Ingalls Peak. And then we have a large amount of sedimentary rocks. Most of the sedimentary rocks are hiding over here in the east. And we're not going to, that sit on top of the Ingalls. They're called the Peshastin Formation. We're not going to talk much more about them today because there's too much to talk about. But when you're driving on Highway 97 and you're driving through the Ingalls Ophiolite, mostly you're driving through the Peshastin Formation, which are Jurassic sedimentary rocks. When you get to the northern part of the Ingalls, around the margin of the Mount Stewart batholith contact metamorphosed the Ingalls. So when you're driving on Highway 97 and you're driving along these sort of gently dipping slopes of argillite and serpentinite, and then all of a sudden you're kind of driving through a canyon with these steep walls of metamorphic rocks all around you. That's because now the sedimentary rocks are contact metamorphosed and they're hornfells, and they're more rigid and they're more resistant to erosion. So in the northern part, as you get closer and closer to Peshastin there to the north, like you're going to go over to Leavenworth or to Wenatchee, the rocks become contact metamorphosed, and then down here, as you get closer and closer to Blewett Pass to the south, the rocks are not contact metamorphosed by the batholith. Then we have another cross section from C to D, which goes south to north. So we have a cross section over here that goes east to west through the eastern part, and we have a cross section over here that goes south to north through the western part of the Ophiolite. And here you can see how the crustal sections are these large faulted blocks that dip steeply to the north, and that most of the Ophiolite is ultramafic rock or serpentinite. These little squiggles are serpentinite. So let's take a look at the ultramafic rocks, or really the mantle of the Ophiolite. To the south, we have harzburgites and dunites. And I have a little, the next slide is a triangular diagram that helps you understand better what is a harzburgite. and what is a lherzolite, because these aren't common terminologies. They're peridotites. Peridotites can be sub-classified based on their mineralogy. And so you have harzburgites and dunites to the south. You have mostly lherzolites, but other units too. There's dunites up here too. Mostly lherzolites to the north. And in the central part, within the Navajo Divide fault zone, because the Navajo Divide is over here, within the Navajo Divide fault zone, you have lherzolites, hornblende peridotites, and plagioclase peridotites that are overprinted by a high to low temperature fault zone. And so they can become mylonitic, or meaning that shearing or faulting greatly reduced their grain size. That's what mylonitic means. Up here is the Clay Elm Ridge fault zone. It's a little confusing. There's a Clay Elm Ridge down here. There's also a Clay Elm Ridge south of Clay Elm. There's too many. There's too many Clay Elm Ridges. But this is the Clay Elm Ridge fault zone up here too. And it has the same general orientation as the Navajo Divide fault zone. So there's these large fault that cuts through ophiolite and separates two different types of ultramafic rocks from each other. Lherzolites to the north and harzburgites to the south. That's going to be important in a second. We'll talk more about that. Over here, you can see Highway 97 coming up through the ophiolite. And there's some letters on here. These letters stand for things. EP stands for Esmeralda Peaks. ND stands for Navajo Divide. I stands for Iron Mountain. K stands for Kings Creek. And S stands for Sheep Mountain. So these are just geographic places that you may or may not know if you're familiar with the area. This is Huckleberry Mountain over here, and this is Hawkins Mountain over here. So this is a classification diagram for ultramafic rocks. Peridotites will have olivine in them, and they'll have orthopyroxene, clinopyroxene, or one or the other. And so you get all these fun names. Dunite is a rock that's more than 90% olivine. Harzburgite is a rock that's mostly orthopyroxene and olivine. Lherzolite is a rock that has clinopyroxene and orthopyroxene and olivine in it. Whorlite is a rock that has mostly clinopyroxene and olivine in it. And then pyroxenites are rocks that are more than 60% pyroxene. And then there are even sub-classifications for types of pyroxenites. And so it can be very confusing. And so when I say harzburgite, I'm talking about a rock that has mostly orthopyroxene and olivine in it. When I say lherzolite, I'm talking about a rock that has clinopyroxene and orthopyroxene and olivine in it. And when I say dunite, I'm talking about a rock that's almost exclusively olivine. All of these rocks are peridotites. So all of these rocks are peridotites. And the peridotite is the mantle. So all of these rocks make up the mantle. So on the previous slide, when we said harzburgite and dunite, it's the mantle. When we said lherzolite, it's the mantle. And so to look at these sections, this is the southern part where we have our harzburgites and our dunites. And this is really cool because it has layering. And so these are layers of pyroxene-rich and olivine-rich harzburgite. So again, the harzburgite is mostly orthopyroxene and olivine. And then this layer right here that's weathering out more easily, that's dunite. And you can think of it as a dike of dunite that cuts through the harzburgite. The dunite is really cool because what the dunite represents is the residue that's left behind after the rock has been partially melted, because the mineral that likes to partially melt in an ultramafic rock is the pyroxene. So when you partially melt out the pyroxene, all you're left behind is the olivine, and so then you left behind with a residue of dunite. And so here's some harzburgites from the southern mantle portion of the ophiolite. If we go into the central portion, you can see a strong foliation running from the left to the right. These pictures are from Bob Miller's doctoral thesis. This is a mylonitic hornblende peridotite. Mylonitic meaning that shearing or faulting has greatly reduced the grain size. The grain sizes have been literally crushed by faulting or shear. And you can see that strong foliation in the rock. That's from the shearing, from the faulting. The mineral assemblages in these mylonitic peridotites that are overprinted by the Navajo Divide fault zone represent greater than or equal to 900 degrees Celsius. It's really hard to get that high of temperature in the mantle by itself in an ophiolite. And so Bob Miller and David Moak in the 1980s interpreted the Navajo Divide fault zone to have formed by a fracture zone setting. And so the Ingalls is interpreted to be a fracture zone ophiolite. And one of the clues that tells you it's a fracture zone is the juxtaposition of the two mantle types across that shear zone, where you have lherzolite to the north and harzburgite to the south. You can actually go in ocean basins and you can see across transform plate boundaries, across fracture zones, you see two different mantle sections faulted against each other along these transform plate boundaries. So this is just a cool picture showing thin sections in plain polarized light and how the shearing has greatly broken the minerals apart. And so here's a much larger orthopyroxene, and then all the little olivines orthopyroxenes are broken apart, and you can see the strong fabric running from the left to right. And then here you can see the plagioclase peridotite sort of broken apart and faulted. The fabric's not as strong on this rock, though. The foliation's not as strong. So now we've moved into the northern mantle section, and here's just a picture of the lherzolite in the northern mantle section. So this rock has orthopyroxene, clinopyroxene, and olivine. If you were to look at this picture, and then you look at the picture of the harzburgite, they just kind of look like orange rocks. They don't look any different from each other. You can't really just look at them and go, oh, well, this one's a lherzolite and this one's a harzburgite. You actually have to look at thin sections and then identify what kind of pyroxene they have. And then you can classify them as a harzburgite or a lherzolite or something like that. The pyroxenes are more resistant to erosion. So it's this sort of lumpy, bumpy texture. That's the pyroxenes weathering out. And the olivines more easily eroded. So olivines making these sort of these little gullies in between the pyroxenes sticking out. This picture is taken very close to Ingalls Lake. So if you ever hike over Long's Pass and towards Ingalls Lake, this is what the rock looks like. And it's very close to Ingalls Peak too. These ultramafic rocks are metastable. They form in the mantle, and they like to be at very high pressures and temperatures. So at the Earth's surface, they're really easily altered into a metamorphic rock. And that metamorphic rock is called serpentinite. Serpentinite is still an ultramafic rock, but it's the peridotite here on the left. And through the process of serpentinization, or altering the rock with water, you're going to turn it from a peridotite into a serpentinite. So peridotite turns into serpentinites through low temperature alteration by reacting the rock with water. The formula of serpentine is D3Si2O5 with an OH. The D is normally magnesium. So pure serpentine is a magnesium silicate with water. But you can substitute iron, nickel, manganese, aluminum, chromium, zinc. Any 2+ cation can substitute into that first cationic site. So that's the mineral formula for serpentine. Normally that D is magnesium. That's why the magnesium is listed first. If it's pure iron silicate with water, it's got a funny name. It's called greenolite, which is not a very original name. It's green. But it's not that common, because what happens during serpentinization is the iron gets liberated from the minerals, and it normally makes magnetite. So these are pictures of serpentinized peridotite from the Ingalls Ophiolite. Here you can still see that relic texture. Sort of the bumps and lumps are still there, but they're gone. They're now erased and turned into serpentine. Both the pyroxene and the olivine can turn into serpentine. And over here is more common serpentine, because serpentine has such a low hardness. It's very easily faulted and foliated and gets this sort of waxy, slick-sided appearance with these mineral slip fibers all over it. And so here's just a highly sheared serpentinite. And then another thing that happens in the Ingalls is you'll have these serpentine barrens, where it's not like a person with a mustache that like builds trains. it's an area where there's no vegetation, and you'll walk through the woods and you have all these nice trees, and then all of a sudden you'll open up and you'll just have some grasses, and uh, and it's because the serpentine has a much more alkalic soil, and the trees don't really like it. There's an endemic um, grass that grows in the Ingalls Ophiolite and the Wenatchee Mountains that really doesn't, that as far as I know, I'm certainly not an ecologist, but I don't think that grass grows anywhere else in the world, and it only grows on these alkalic soils, on these serpentine soils in the Wenatchee Mountains that form in the Ingalls Ophiolite. It's not, it's not very exciting. It's just a grass, but it's something, right? Okay, good. Well, why do we care about serpentine and other ultramafic rocks? This is a picture put out in the early 2000s, I believe it's 2012, by the United States Geological Survey. And what they were doing was they're identifying areas of large amounts of ultramafic rock, because you can take ultramafic rock and you can sequester carbon dioxide with it. What you would do is you would take, I have the next slide shows that. So all little black blobs on here are areas in North America where you have large amounts of ultramafic rock. And there's Josephine Ophiolite. Here's all the Coast Range Ophiolites. There's the Smartville Ophiolite. There's our Ingalls. There's our Fidalgo, the Twin Sisters, those little bits and pieces, so the Hell in a Haystack mélange. So there's all these ultramafic rocks that occur in Washington State, and they have a potential to sequester carbon dioxide. How in the world would they do that? This is just a picture of serpentinite from the Ingalls Ophiolite. You can see how there's not a lot of vegetation because the plants don't really like it because of the alkalinity of the soil. And so the silicate minerals can be converted into mangasite, which is a magnesium carbonate. So if you take the serpentine, magnesium, silicon, and oxygen, you add the carbon dioxide that you've captured from your power plant, and you chemically combine it with the serpentine. You got to add some energy. You got to heat it up. You'll make mangasite, which is a magnesium carbonate, quartz, and then you'll make water because of the OH and the serpentine. The quartz comes from the silica, and then you make magnesium carbonate from the magnesium and the carbon dioxide. Mangasite is a carbonate that's not readily soluble. It's not like calcite. You can't just put hydrochloric acid on it and react. It takes a really strong acid to dissolve mangasite, much stronger than calcite. And so it's truly sequestered. And so there's a potential for the ultramafic rocks in Washington State to have an impact on sequestering carbon dioxide to try to help global emissions of greenhouse gases. So that's really cool. There are these weird rocks. This is a picture along Highway 97. If you look really carefully, that's a tall boy can that was some terrible person threw into the Peshastin River. But I thought, oh, great. Okay, there's a scale. So that's a 16-ounce can of beer that's now lying in the Peshastin River. These white colored rocks that are running through the serpentine, the rest of the rock is serpentine, is called rhodonite. They're basalts or diabases that chemically reacted during serpentinization. And they have hydroglossular and other funny minerals in them. This orange rock right here, that's above the Drew Creek. So there's Mount Stewart in the background. There's Esmeralda Peak in the mid section. This rock's called listhonite. And listhonite is essentially a siliceous carbon dioxide rock that forms when carbon dioxide and water chemically react with serpentinite. And then this is an ophiocalcite. And you can see these funny little breccia pieces through here. Those are serpentinite. This is calcium carbonate that got captured when carbon dioxide was sequestered by the ophiolite. All three of these pictures are showing natural ways that ophiolites can sequester carbon dioxide. So that's really neat. And you see them in ophiolites all over the world. People have been studying Oman as a potential place where they've been injecting supercritical CO2 into the earth to try to sequester the carbon dioxide. So, so this is just a neat side note about some of the things you can do with ultramafic rocks in ophiolites. So we studied the serpentinites, Scott Milliken and myself, and we chemically analyzed them. This is SEM image. That thing in the middle is serpentine. All these really bright colored things are pyrite and other sulfides. This is a scanning electron microscope image. And then we used an electron microprobe and we chemically analyzed the serpentine. And this is our data. We have aluminum substituting for our silica. And we have iron substituting for our magnesium. So if we were to write a chemical formula for, we also have iron and nickel substituting in for our magnesium. So if we were to write a chemical formula, it would be a magnesium-rich serpentine, but it would also have a little bit of iron and tiny bits of nickel and chromium substituting in for the magnesium. And then we would have aluminum substituting in for our silica. And so we wanted to know what kind of what the chemistry of the serpentine was. And I've done other studies to identify that most of the serpentine is the polymorph lherzolite, but there's a little bit of chrysotile in there too. Serpentine is 3 polymorphs: antigerite, lherzolite, and chrysotile. Antigerite forms at the highest temperatures, chrysotile forms at the lowest temperatures. They all form at very low temperatures though. We also did the whole rock geochemistry of the serpentine to try to infer which kind of ultramafic rocks were metamorphosing to form the serpentine. And so, for example, most of them are harzburgites or lherzolites. And again, harzburgites and dunites and lherzolites. And so that was kind of a really neat way to look at it and try to infer about where the serpentinites may have come from. And then I wanted to know if the serpentinites were behaving like rocks from the mantle were, or if the serpentinization greatly affected them. But chemically, they look like, oh no, the serpentinites are really remembering their original geochemistry, and so so they're behaving well. So we can actually look at the geochemistry of serpentines and make some questions about the original tectonic setting. And so that's what this picture over here on the left, or I'm sorry, on the right is doing. So a lot of them are abyssal peridotites. Abyssal is just fancy talk for mid-ocean ridge. So they formed at a divergent plate boundary, but we also have an arc component, so a subduction zone component. So the peridotites seem to be transitional between mid-ocean ridges and subduction zones. And we're going to find out that's the same thing as the crustal rocks. So let's quickly transition over to the crustal rocks. Let's look at the Iron Mountain unit first. The Iron Mountain unit is this sort of dark gray unit all through the southern portion of the ophiolite. So we're going to zoom in over here. Iron Mountain unit is named after Iron Mountain proper. There's some more rocks over here. And then it forms over here also through Sheep Mountain and up through Kings Creek. We have a zircon uranium lead age of 192 million years, so it's early Jurassic. The Iron Mountain unit is made up of these spectacular pillow basalts. In that circle, there's a little tiny rock hammer, and so these are beautiful pillow basalts that you can find within the Ingalls Ophiolite. If we zoom in on these pillow basalts, we can see that there's the pillow basalts are formed underwater from volcanic lava flow, and it has limestone formed in between the pillow basalts. We also have a lot of hyaloclastites or pyroclastic rocks that formed. So when the lavas were erupting, they were breaking apart and forming glass at the bottom of an ocean basin. And then there's a large amount of limestone that's associated with the Iron Mountain unit. Here's a large piece of limestone that's just north of Iron Mountain proper. And then in the background here are basalts. These are basalts in the foreground where Ante is standing, and here are dikes coming off those basalts, and they're intruding limestones. And if you look at the limestones, they're oolitic, which means they're shallow water limestones. And so these limestones are actually forming in a tidal area where the grains were washing back and forth. Now let's look at the Esmeralda Peaks rocks. And so if we zoom in on a map over here and a map over here, we can see Esmeralda Peaks proper. So there's the North Fork of the Tianaway River. The Esmeralda Peaks Basin Trailhead Parking is just over here somewhere. We have mostly volcanic basalts and pillow basalts on the northern part of Esmeralda Peaks. This doesn't hold true everywhere. And a lot of diabase and gabbro on the southern part. Over here, along Ingalls Creek Trail, along the Ingalls Creek, on the eastern portion of the Ophiolite, we got a uranium lead age of 162 million years old. So that's late Jurassic. So the Iron Mountain unit is early Jurassic, 192 million years old. The Esmeralda Peaks unit is late Jurassic. So here's just some lithologies. These are some pillow basalts that you can find in Esmeralda Basin. This is really close to the parking for Esmeralda Basin Trailhead. This is the North Fork of the Tianaway River. This is hydrothermally altered chert that's now altered to epidote and surrounding the pillow basalts. I like this picture because the little pillow basalts are back underwater whence they came. I always thought that was kind of fun. You also get what are called isolated pillow breccia, which just means you have little pillows that don't touch each other. They're touching sedimentary rocks instead, and the sedimentary rock is chert that they're touching. And then you have pillow breccias too, which the pillow basalts broke apart when they erupted. So it's a kind of pyroclastic rock too. Then you have the diabase. And here's one of the rare places where the diabase is actually in dikes, and I outlined the dikes in white. But most of the diabase is massive. This diabase is so cool, it had to wear sunglasses. Most of the diabase is very massive without dikes. Then you can transition from one unit to another. There's gabbro, screen, which means a little bit of gabbro that the diabase intruded. So there's diabase on either side. This is faulted with a lot of low temperature alteration minerals cutting through it. But there's a diabase dike that was cutting through gabbro. It's got a little normal fault on it now, but there's the dike that was cutting through the gabbro. So we're transitioning from the diabase into the lower magma chamber unit. And then here's gabbro, sort of a massive gabbro with a pegmatitic gabbro dike that cuts through it, and then a little mafic layer that cuts through it as well. We also have felsic dikes that cut through the gabbro as well. And the dikes are these sort of odder igneous rocks called tonalites and trondhjemites. So they're like granites, but they don't have either any or very much potassium feldspar in them. So they have mostly plagioclase and quartz with hornblende. So geochemistry. The big thing that's important here for the Esmeralda Peaks unit is they're enriched in thorium, but they're depleted in tantalum and niobium. And what in the world does that mean? Well, it means when you partially melt the mantle to make magma at a divergent plate boundary, thorium, tantalum, and niobium all go into the magma. They don't stay behind in the mantle. But then when you're subducting oceanic crust, the tantalum and niobium stay in the subducting crust, but the thorium comes out and gets enriched into the asthenosphere. And so thorium is one of the volatiles that leave the downgoing plate in a subduction zone and enrich it. So when a rock forms in a subduction zone, you'll get an enrichment of thorium over tantalum and niobium, and you'll get this sort of this depletion in tantalum and niobium. And you can see it in all of the late Jurassic Esmeralda Peak rocks. Here are some modern rocks. This is an island archeolite from a modern tectonic setting, and you can see that depletion between thorium and tantalum and niobium. TH is thorium, TA is tantalum, and B is niobium. Where an ocean island basalt that would form at a hotspot doesn't have that depletion. And when we look at the early Jurassic Iron Mountain unit rocks, we see that they're transitional between E-morb and ocean island basalt. And E-morb is just a mid-ocean ridge basalt that's enriched. And so they don't have a subduction component, where the late Jurassic rocks do have a subduction component. And so we have rocks that are two different ages, and they formed in two different tectonic settings. So that's really interesting. These diagrams just show the same thing. They show that the Iron Mountain unit samples here that I'm outlining are closer to ocean island basalts, where the Esmeralda Peak units are transitional between Morb and arc components. These diagrams show the same thing. So why show so many diagrams? Well, I don't know, just to stress the point. So there's our early Jurassic Iron Mountain units, and here's our late Jurassic Esmeralda Peak units. And early Jurassic is transitional between enriched mid-ocean ridge basalts and ocean island basalts. Ocean island basalts are hotspots. Enriched mid-ocean ridge basalts are divergent plate boundaries that are near hotspots. And then the late Jurassic Esmeralda Peak unit is transitional between normal mid-ocean ridge basalts and arcs. And they all have that subduction zone component, that thorium, niobium, tantalum depletion. We'll skip this. That's okay. Running out of time. So here's our little tectonic interpretation. During the early Jurassic, the Iron Mountain unit formed near a divergent plate boundary. And it's a hotspot. And we know it's a hotspot because of its lithologies. It has pillow-basalts and hyaloclastites. If you go to Hawaii today, you find pillow-basalts and hyaloclastites. It has massive flows, and it has limestones that formed tidally, that were influenced by the ocean lapping back and forth. So clearly, those limestones formed fringing a little ocean island during the early Jurassic, about 192 million years ago. The chemistry suggests that we're near a divergent plate boundary. That's why they're enriched mid-ocean ridge basalts transitional to ocean islands. Sometime after the Iron Mountain unit formed as a hotspot near a divergent plate boundary, they approached a subduction zone and they got sort of faulted onto a continental margin. That continental margin during the late Jurassic rifted apart and formed an ophiolite. It formed the Esmeralda Peaks unit, the late Jurassic ophiolite. And that ophiolite formed above a subduction zone, a supersubduction zone. And its chemistry is influenced by both the divergent plate boundary from shallow melting at a divergent plate boundary, but it also is being enriched by fluids like thorium from the subduction component. And the serpentinite geochemistry mimics that same. It's a transitional between a divergent plate boundary and a convergent plate boundary. I think I'll stop there. I have more slides, but I've already gone over time. Would anyone like to ask me any questions?
Yeah, if you want to go finish your slides, that's fine. But are there any other questions? I had a few questions, but
yeah, I do too.
Oh, well, let's just do questions instead. The questions are more important.
That's good.
Yeah, I was curious about the nickel and chromium and whether the deposits are economic and what the source of the mineralization is.
Oh, so you were talking about the nickel and chromium in the serpentinite.
Yes, correct.
Oh, there's only trace amounts of nickel and chromium in it. They're less than a half a weight percent. They're very little amounts. However, what I didn't show you is the mantle, especially the harzburgite and dunites in the southern portion of the ophiolite. They have chromite in them. In some places, a large amount of chromite. Chromite is a chromium aluminum oxide. It's a spinel group mineral. And so there is a large amount of chromium in the mantle rocks. And that's pretty typical. In ophiolites, you get chromite and sometimes what's called pod form, which are big blobs of chromite rock forming. Is there enough to be economical? Probably not, unless we get desperate. However, if you've ever been to the Ingalls Ophiolite, you'll know that most of the ophiolite, or a portion of the ophiolite, forms in the alpine wilderness area, so can't mine there. And then the rest of the ophiolite is in very rugged terrain, so it's very difficult to get to. It's in a national forest. Not that you couldn't mine in a national forest, you could if you really wanted to. But it would be very expensive, and there's not that much. Some of those lisbonites, some of those funny orange rocks I showed, if you read really old papers about the geology of places like Blewett Pass, like the gold mining in the 1800s there, they talked about these things that they called nickel dikes. That was the lisbonite, and they had an unusually large amount of nickel in them, and people tried to mine them in the 1800s, and they just didn't get enough to actually make any money. And so you could if you were desperate, but you probably wouldn't because it would be too expensive to mine because there's not that much and it's in very rugged terrain. And then a large portion of the ophiolite is in alpine wilderness, and you can't mine alpine wilderness.
Okay, thank you.
Oh, you're welcome.
Thanks,
Please
Judy.
ask more questions. I'm
Is
ready.
there anyone else? I do have a question to add, but I want to see if anyone else, and if you do, it would be great if you show your camera too, so we can tell who's asking and who you are.
Hopefully everybody could follow everything I was talking about. I probably had too many background slides, but that's okay.
Oh, I thought it was great.
Oh,
I
wonderful. Thank you.
learned a lot of stuff. I thought, like I learned geology a long time ago, and wow, things have changed.
Yeah.
How
Hey,
about if
yeah,
I
it was good to
try?
get a review and an update.
Yes. Now I have a question. I don't know if you'd be willing to put up one of your last pictures. You showed cross section with the spreading ridge and the island arc
Absolutely.
and things like that.
Absolutely. So this slide right here, right?
Yeah, that one. Okay, so I'm just thinking in context of, all we've heard about the island, the ribbon continent, for example. Now take your upper left picture there. I'm wondering, like, is there a way you could tell whether those, such as Iron Mountain or the others, might have been produced on an arc that's a ribbon continent? Like, I don't see how you can tell whether it's an island arc. I know Rob Hildebrand talked about this too. Was the island arc over on a continent versus one on oceanic crust? And
You
then,
can tell.
yeah,
You would know that through the geochemistry. When the basalts were coming up through if they're coming up through oceanic lithosphere, they're not going to assimilate anything because it's just mafic lava moving through mafic crust. If they're coming up through continental crust, the basalts are higher temperature than the more felsic continental crust, so they would assimilate a large amount of continental crust, and the basalts themselves would have more intermediate compositions, or they would just have really funny chemistry. And you don't see that. They're just regular oceanic looking basaltic rocks that didn't really assimilate anything funny. And so they just probably came up through oceanic crust. And then you don't see anything but oceanic rocks. So you don't see any continental rocks mixed in with these besides the sedimentary rocks that sit conformably on top of them. But those sedimentary rocks were derived from of close intermediate composition island arc volcanoes. And we know that from the detrital minerals that are within them, and we know that from their geochemistry. And so the one slide I didn't show, which is the very next slide, is we correlated the Ingalls Ophiolite with the Josephine Ophiolite in the Klamath Mountains for several reasons. They're very similar in age, they're very similar in tectonic setting, and the sedimentary rock sets, the Peshastin Formation and the Gallice Formation, have the identical radiolarian assemblages. And so the fossils that sit on top of these two ophiolites are identical. And so probably the Ingalls formed as a super subduction zone ophiolite, just like the Josephine, down somewhere where the Klamath Mountains are today, and then got accreted or thrust up onto the North American margin, but unlike the Josephine, the Ingalls translated north into its current position, where the Josephine's still down in California and Oregon. So no, the short answer was no about the continental crust.
So you couldn't find any evidence for this ancient riven continent in that.
Not in these rocks, no.
Who knows?
No, the chemistry doesn't suggest that there was a ribbon continent there. The sediments that sit on top of them don't have any suggestions that there was a continental margin close by. And the rock lithologies themselves they're just oceanic rocks. They're basalts and hyaloclastites and oolitic limestones, and gabbros and diabase. There's nothing that's continental about them. They're oceanic rocks.
So what's a current analogy to that? If that came up in the middle of the crust like that.
So oh, I'm sorry, hold on. So I'll share my slide again. And so the Iron Mountain unit, something that's very similar today would be the Galapagos hotspot. The Galapagos hotspot forms right next to the Galapagos Ridge. And the geochemistry of the Galapagos hotspot is influenced by that divergent plate boundary. Then the Esmeralda Peaks, the late Jurassic, this would be basically the same thing that you find in the Western Pacific, and specifically the Southwestern Pacific. This could be the Marianas Basin or the Lau Basin, and this could be the Marianas Arc or the Lau Tonga Arc. And that would be the Pacific plate subducting underneath the marginal basin that sits next to it. And so this is something you see where the Galapagos hotspot forms today. And this is something you can see today in the Western Pacific, like the Marianas Basin or the Lau Basin, or even you can even see it in the Scotia Sea down in the Southern Atlantic as well. So those are modern settings where you would see something very similar. And that's what we like to do. We like to look at the modern oceanic settings and see how our geochemistry and lithologies and rock types which do they correlate best to.
Yeah, that's really great. Does anyone else have some questions?
I'm ready. One other question I had was, because I'm trying to see what would happen with the pillow basalts. What do they look like when they get more metamorphosed? Because I was up around 100 Mile this last week, and we saw this erratic that was, oh my God, it was pillow basalt, and it was out in the middle, like probably comes from the intermontane region, which I'm not so sure where the Ingalls fits into that or not, but I think the Ingalls is what they would call in Canada the insular, or is it what they call intermontane? It doesn't fit into either of those two terranes. It's actually thrusted over the insular terrain. It's the wrong age. It doesn't fit into any of these large terrain models. And it's physically thrusted over one of the intermontane terrain, I think. And so it's a translated terrain. It moved from the south to the north. It might not have moved as far as those terrains did. And it doesn't fit neatly or nicely into those terrains. It geologically stands out, and I don't think it's the right age for those terrains either. But metamorphosed pillow basalts can have all sorts of different appearances. They can really just look like pillows, and they can be weakly metamorphosed, or even if they're highly metamorphosed, they can still basically be very bulbous and elongate and sort of cool looking. Alternatively, if you ever go up to Mount Shuksan or look at the Shuksan green schist and blue schist, those are metamorphosed basalts, and some of them will have pillow structures in them, and the pillows can get elongated almost like a stretched pebble conglomerate. Pillows can become flattened and elongated, or they can lose their texture altogether and just become greenstones or green schists and things like that. So a green schist or a green stone is just metamorphosed basalt. And so is amphibolites. There are amphibolites in the Ingalls Ophiolite that are metamorphosed gabbros and basalts. So they can look like all sorts of cool stuff. But if you can still see that bulbous structure, then it hasn't been that heavily deformed. Even if it's in green schist facies metamorphism, it was sort of static. It was higher temperature without a lot of pressure. Once you start to get pressure, then you start to lose those bulbous pillow structures because you start to get a foliation, and the foliation kind of erases the pillow structure.
Okay. But it is possible there that there was transport even there from the southwest to the northeast, from the east side of the coast range into. It's kind of odd that there is some evidence that the glacier and the peak may have flowed over. So it might have taken it off those units that are similar. I think the Bridge River would be similar to what you have, but there's also the Cache Creek. And so there's some other ophiolite looking features that we're going across.
Yeah, and like somebody said earlier, they're oceanic rocks that are just like the rocks you find out in the Olympic Peninsula. You have all those massive and pillow basalts and stuff, and essentially that's those are the upper parts of an oceanic lithosphere and crust because they have to form underwater because they're bulbous, right? And that's where pillow basalts form. They form underwater, and so you get sort of slices of them. You see the same thing in the western mélange belt and the eastern mélange belt. You have pillow basalts, but you don't have this lithology. You don't have all the other. You do have them, but all sort of folded and mixed it together. But you don't have this nice little sequence that you would have, say, in the Ingalls. Or even the Fidalgo. The Fidalgo has pillow basalts, and then it has this odd sort of Jurassic arc that cuts everything, that kind of hides where the diabase would have been. And then it has the gabbro, and then it has the mantle out on the San Juan Islands there.
That's terrific. I have two more. I'll try to be quick, and someone else could ask questions. One
Please.
is the mineralogy we would expect from it. Now, I know the ophiolite that is on the west side of the Sierras. We did a GSA field trip there, and it was very interesting that there's a lot of gold there, and just the idea of why would you perhaps get gold, and what other minerals might you get in that area?
The gold, when I first went out to the Ingalls, I didn't really know where the gold was coming from either. I assumed it was coming from the ophiolite, but it probably isn't. The gold's probably coming out of the Eocene rocks that like the Teanaway Formation and the Teanaway Dikes and the Wenatchee Dome, all these weird Eocene igneous rocks that form in the 40s. And so the gold's probably associated with these Eocene rocks that also cut through the Ingalls Ophiolite or sit on top of the Ingalls Ophiolite. The ophiolite itself is its primary mineralogy would have been pyroxenes and amphiboles and plagioclase feldspar, and the plagioclase probably would have been andesine, so sort of on sodium-rich end member, not calcium-rich end member. But most of the ophiolite is now metamorphosed to green schist facies, and so you get all these chlorites and some actinolites and a lot of epidote and a lot of grungy green things. And the poor plagioclase has all the calcium sucked out of it, and so it's all been what we call albatized. It's the sodium end member, and so in all the glass has been altered to clays and sort of brown gunk. And so, mineralogically speaking, the rocks are they're low temperature to moderate temperature, low pressure to moderate pressure alterations to what you would say green schist facies metamorphism. Then to the north, it transitions into amphibolite facies metamorphism. So you got amphiboles and plagioclase and quartz. But then the ultramafic rocks are olivines and orthopyroxenes and clinopyroxenes, and there's lots of spinel, lots of oxides. where they've been metamorphosed, the ultramafic rocks, you have serpentinite and magnetite, and you get weird sulfides, nickel sulfide, cobalt-rich sulfides, iron sulfide, obviously. And there have been some reports, I've never seen it, but in some of the old mining reports from the Blewett Pass area, they say there's malachite. Well, I've never seen it though, but they say there's some copper in there too. And so there's all sorts of, it's a very eclectic, there's lots of stuff in the ophiolite. It's an eclectic collection of rocks and minerals. And then you get these pod-formed chromites too, which are the oxides that you get in the ultramafic rocks.
We used to hike up to Malachite Lake, so there is malachite in the Alpine Lake.
It's been reported, but some of these reports are quite old. They're from like 1930.
Yeah. What I was familiar with, mineralization is important, of course, now, because that's often what drives the hiring of geologists, and geologists, at least in BC, are told your job is go out and find minerals. And if you happen to figure out why they're there, that's great, but we don't want to know that. We want to find the minerals. It's just kind of, I don't know.
I would conjecture that the most important mineral in the Ingalls is the serpentine, because that serpentine has that sequestration potential. And the serpentine is easy to find.
Well, sequestration for carbon in the atmosphere, right? Carbon dioxide.
Yeah.
That's what you mean. Yeah. Well, just to the east of there or north, there are very big open pit copper mines. I know they're in BC, and it goes, I think, down into Washington, and they're also in Idaho and other areas. But they were originally batholiths or island arc systems with hydrothermal circulations. So
they're different. They formed it.
We don't have anything like that in the Ingalls, because they were just, yeah. Maybe if you could explain the difference a little bit, because it's really quite different.
Oh well, yeah. It's not. Those porphyry deposits form where magma sends a lot of magmatic and hydrothermal water into the rocks above, and it leaches out a lot of metals and things like that. The Ingalls never did that, because when it formed at divergent plate boundaries, the temperatures aren't as high, and it doesn't have the kinds of metal enrichment in the original magmas that you would have in a continental setting, where you have those other arcs, in which were continental arcs, not an oceanic arc. So in these oceanic settings, you don't have nearly as much interesting stuff that you pick up in the magma as it moves through the crust, because it's just mafic magma, which sounds simple, but it is, and it's rich in other things. It tends to be rich in chromium. It tends to be rich in vanadium. It tends to be rich in scandium, as opposed to things like copper and platinum and gold and stuff like that.
So I mean, some of those are rare. Maybe you could comment about the rare earth element implications, because people are looking all around the world for that, like in the Ophiolites, and what could you learn from that?
I don't know that much about them. They tend not to be super enriched in rare earth elements. They tend to actually be depleted in rare earth elements. They tend to be more enriched in the lighter rare earth elements, things like lanthanum and through europium. Because they're normally hydrothermally altered in an ocean setting, a lot of these things, especially europium, tends to get weathered out and things like that. But the best potential would be in the plutonic rocks, in the gabbro. The gabbro will have a lot of pyroxene. It will have, which can have nickel and chromium. The gabbro will have a lot of plagioclase feldspar, and the plagioclase could have europium in it. Not a lot, though. And then in these ophiolites that form the subduction zones, they'll have amphiboles in them. And the amphiboles could potentially have rare earth elements, although they tend to be pretty straightforward hornblends. They tend not to be the special kinds of amphiboles you would get a lot of rare earth elements in. And the pyroxenes tend to be pretty run-of-the-mill pyroxenes too. Like, they tend not to be lithium rich or anything like that. They tend to just be iron, magnesium, calcium, pyroxenes.
Your work's really interesting. I have two other questions, and one is from what, and I'll ask both of them, and then won't be quiet. One is, since this was happening in the Jurassic, early Jurassic,
One part's the early Jurassic, the other part's the late Jurassic.
okay, so can you tell, compared to the current time, how the Earth's interior and the mantle composition has somehow changed, or something in it, or even temperature has changed? And then the second is, any advice you have to help people who might want to do a job like you, and what kind of skills and classes, and like, how does someone get to be a professor like you are and be able to figure these things out? Like, what would you advise them?
The first question is, the rocks are pretty similar to the rocks we see today. And so the Jurassic mantle looks pretty similar to the mantle we have today. The Earth's 4.6 billion years old, right? And the Jurassic was only 190 to 150. These rocks that are only 190 to 150 million years old. So, 4.4 billion years passed. And so most of the interesting things that happened to the mantle that changes composition had already happened by the time the Jurassic comes around. And so the one thing I can tell you is the chemistry of these rocks are very similar to identical to the chemistry of rocks you find today in modern tectonic settings. And so the mantle in the Jurassic seems to be pretty similar to the mantle we have today. So what did I do? Well, the easiest thing was to be a geology major. That's number one. And so I was an undergraduate geology major. Well, I didn't know any geologists when I was growing up. Most people don't. And so the only people I knew who were geologists were my earth science teachers. I grew up in New York State, in the suburbs of New York City, about 80 miles north of New York City. And in New York, we have to take earth science in high school. I really liked it. And like many children, I used to go mineral collecting when I was a little kid. So I really liked minerals. I liked mineral collecting. And then I really liked earth science, quote unquote, in high school. So I thought, well, I'll be an earth scientist, not knowing what earth science really was. And I thought, well, what do earth scientists do? Well, they teach high school, so I guess I'll have to teach high school. And so originally I went to college to be a secondary education earth science major, which I hated. So the teaching classes were a struggle for me, which is ironic because now I'm a college teacher. So I changed my major from earth science to environmental geology, because in New York State in the 1990s, when I went to college, you had to have a dual, when you were an education major, you had a dual major. And so I was a dual major in education and geology. So it was easy for me to just change over. So the first thing I would suggest is, if you're interested in geology, please excuse me, take geology classes, be a geology major, go back to college to be a geology major. That's number one. Then be lucky. I had a lot of people who were encouraging and supporting. So find someone who is encouraging and supporting. Don't waste your time on people who aren't. And they were telling me, oh, you're really special, you're really gifted, you should go to graduate school, which I had no idea how to go to graduate school. So okay, well, I guess I should go to graduate school because all these professors keep telling me I should. So find someone who you feel would be very encouraging, and ask them whether or not graduate school would be a good opportunity. And if they say yes, go to graduate school. And you don't have to be a super genius to go to graduate school, because I went to graduate school. And then when I got to graduate school, I really lucked out, because Greg Harper was a wonderful man, and he was encouraging and would tell me how well I was doing all the time. So I really lucked out, because lots of times you'll hear all these horror stories about how the graduate advisor was a monster and things like that. So be lucky and find a graduate advisor who, again, is encouraging and nurturing. and generous with their time. And then just work really hard. You don't have to be smart to do this. I'm not smart. I'm not curing cancer or you know, all the ails of the world are solving because I've studied these Jurassic Park rocks in Washington State. Just be interested in solving problems and practice the scientific method and ask the right questions and then with enough time and stick to itiveness, you can do it too. If I can do it, anyone can do it. Go to graduate school, take geology classes, be curious, and then find out who knows to ask questions that you want to ask, and then surround yourself with those people. That's the best I can do. That was a long answer, but
Thank you. Oh, you're quite
Well-
humble, but you are quite great. Oh, thank
Well,
you.
I'd like to say that I really admire that you've managed to have a research area in a part of the country that isn't horrifically hot and humid, even
yeah.
though it's in Florida now.
Everyone likes to
Well
ask,
done.
what's this guy from Florida doing coming out to Washington State? And it really is because my advisor had a grant with Bob Miller. Greg Harper had a grant with Bob Miller, and Greg studied Ophiolites, and so we went across the country, and there's a lot of really interesting geologic problems in Washington State, and people just weren't working on them. So it was easier for me to just continue working in Washington State than it was to try to find a whole new research area in the Southern Appalachians or something like that. So just kept going out to Washington.
We have airplanes.
Yeah, sure.
What do you think? What are you planning to work on next, or what do you think is a problem that needs to be explored in the future?
For me or for geology?
I don't know. What do you think is interesting? Like maybe there are things you've learned. You always learn new things when you try to solve something. I'm not saying to give away your secrets on this, but like if we give you another 30, 40 years and you've got a bunch of students and money, what kind of things would you try to do?
I would keep working on the Jurassic tectonic development in Washington State because I'm very interested in the really Mesozoic tectonic development in Washington State. The Rimrock Lake Inlier in the southern part of Washington, which is in the Columbian Bayment. It's not supposed to be there. It's not supposed to be basement rock in the Columbian Bayment. That's a fascinating place. Somebody needs to go down there and solve a lot of problems. It's essentially the basement rocks that Mount Rainier comes up through, in the rocks that are associated with Mount Rainier. And somebody needs to figure out why plates move. Gravity, they move because of gravity. But the mantle has a major effect on why plates move. And if you take all the forces of gravity and then you take all the forces of friction and you add them all up, lots of times the friction wins. Not always, but many times. And so the mantle must have a dynamic effect on plates. And so we need someone to figure that out for us. That would be great. Thank you. And then climatologically speaking, we need people to study the climate to understand past climate changes and how rapid or slow did they occur, and think about things that are happening today and help put them into perspective.
Well, all right. Well, if there are no more questions, thank you very much, Janie. Hang on a second. We give out speaker gifts.
Oh,
And
my hand, so take it.
what we like to give are we have two choices, and one is a hat.
Ooh, it's an excellent hat.
They also come in kind of dark charcoal, and the other, if it's more useful for you, and Mindy has one, is an insulated tumbler for travel. So let me know which you would like, and I'll have it shipped to you.
Thank you. I guess the tumbler. I'm not
Okay.
really a hat guy, but
Yeah.
I would be and to have the Association of Women Geoscientists tumbler would be an honor.
It's
Great.
great and it's
All right.
unique.
Yeah. Everyone would be jealous. And it was my
Yeah.
pleasure. I'm really flattered to be asked, especially by AWG and the Pacific Northwest section. So thank you. It's my pleasure.
It's a great talk, and you've got so much information. It'll be really helpful. I'll probably have to watch it again, and I'm sure others will.
Too much information.
I'll let Marcia end off.
All right, well, I'm going to stop the recording.